All right, welcome everybody. So in this video, we are going to use what we've derived about the solution to least squares problems. And we've talked about how those solutions are exactly equivalent to finding a best model for some data that we want to fit to a linear model. So the example that I want to take a look at is, well, let's imagine that we collect a sample of data from 4 countries. Okay, this is a small sample, but here I want to type these matrices and vectors on a slide. And we record the most recent data for each country's GDP per capita, and that's what we're measuring in this observed vector of y values. So that's our response variable is the wealth, which is GDP per capita. And we've observed the literacy rates for these 4 countries that I've recorded down this column over here. So this is telling me that for one country, their literacy rate was 31% and their GDP per capita was about $2,000. So here we're giving GDP per capita in thousands of dollars. And here's another country, their GDP per capita was $13,000 and they had a literacy rate of 98%. And our goal is to fit a model of the form y is equal to beta 0 plus beta 1 times x1, where x1, again, is the literacy rate that we've observed, and y is the GDP per capita that we're trying to predict. And we can represent this system of equations for all 4 of these observed values as a matrix equation where we want the response variable y, GDP per capita, to equal a matrix X, this what we call model matrix where our observed data is. And this first column of ones again is because our model contains a vertical intercept, which has a coefficient of 1 in front of it for every observation. And we're going to write this as this model matrix X times this vector of coefficients. In this case, we've got 2, beta 0, beta 1. And on the other side, we're going to set that equal to y, which is the response that we are trying to predict. And so this is equivalent to solving a least squares problem, since the goal here is to minimize the sum of the errors squared. That's going to give us our best model. That's how we're defining the best model. And to solve this, recall we have these normal equations that we can solve. And so I can multiply both sides of this initial equation by x transpose. And now x transpose x is a square matrix, even though x may not be a square matrix. So we might be able to invert this as long as the product x transpose x is invertible. And from the inverse matrix theorem, we know that this product x transpose x will be invertible as long as the matrix X has a pivot in every column. And in this case, we can see very clearly that these 2 vectors are linear, these 2 column vectors of matrix X are linearly independent from each other. One is not a multiple of the other. So we're going to be able to invert this matrix. So if I want to solve this regression problem, then the first thing I can do is identify what the product of X transpose X is. So here's the matrix X transpose, where the first row of this matrix is all ones because the first column of X was all ones. And then our second row is our row of observed literacy rates. So I'm going to take X transpose times our model matrix X, and out comes a square 2x2 matrix. And this matrix, the product of X transpose X, we can see here, this happens to be a symmetric matrix, and we're going to discuss shortly some really nice properties that we can use with symmetric matrices that might help some of these calculations. But for now, X transpose X, this happens to be, in this example, a 2x2 matrix, which is invertible. So we can solve for beta now by multiplying both sides of this equation by X transpose inverse. So here was the product of X transpose X, and now we're going to take the inverse of that matrix times X transpose times Y. So recall that in general, the solutions here, when we can invert this product of x transpose x we get by calculating this product of matrices and vectors. And all of these calculations, by the way, I've done in a Google Colab notebook, which is linked in the description to this video. So you can play around with that notebook and double check these calculations. But out comes a vector, which has first entry minus 1.938 and second entry is 0.126. So here's the solution to this least squares problem, which happens to give me the best model in the sense that it minimizes the error of our predictions. So therefore, we've got the following equation that the wealth, the GDP per capita, is going to equal, the intercept here is minus 1.938 plus 0.126 times whatever value we observe for the literacy rate. So I'm calling this education. And I put a little hat over the wealth because what we're calculating here is not the actual wealth of some country that has a certain literacy rate. We may not know what their GDP per capita is, but what we're calculating is our best prediction for what their GDP per capita is. So when we're indicating predicted values, we put hats on top of the Y value. In this case, we put a hat on top of wealth. And then ultimately, what we'd like to do with this model is interpret this relationship. So for example, I can see that this coefficient is positive. The slope is a positive value. So this is telling me as the literacy rate goes up, I should expect the wealth, the GDP per capita of the country on average to go up as well. But we'll take a look on the next slide about how we can make use out of these models to make predictions and interpret what these coefficients are telling us.